Hello students, uh, welcome to the lesson. Sorry I cannot be there next to you to present this lesson for you. Right? This is the VCA video for forces. Right, so we're going to go through some of the concepts that we have learned in secondary school and try to bridge your knowledge for some of the things you need to know for A-levels. So first of all, as we all know, a force is either a push or pull. Force is either a push or pull, right? And one of the key things we need to learn in A levels is about the concept of equilibrium, right? So let's start with the definition. A body is in equilibrium when it is in translational equilibrium. What does this mean? What does translational equilibrium mean? It means that the sum of the forces on the body is zero. A second condition for a body to be in equilibrium is that it must also be in rotational equilibrium. What does this mean? It means that the net moments about any point is zero. Okay, so one more time in total. A body is in equilibrium when it's in translational equilibrium, where the sum of the forces on the body is zero, and when it's in rotational equilibrium, where the net moments about any point is zero. Right? So we'll talk more about what is translational equilibrium and rotational equilibrium in the rest of this lesson. When a body is in equilibrium, by Newton's first law, it will either be stationary or moving at constant speed. Right? This is one of the key effects of equilibrium. What does this mean? It means also, right, how should you interpret it? If something is at rest, you know that it is in equilibrium. Right? So one more time, when something is in equilibrium, it's either stationary or moving at constant speed. What this also means is that if something is stationary or moving at constant speed, that body is in equilibrium. So the rules of equilibrium will apply. With this, we can talk more in detail about translational equilibrium. A body is in translational equilibrium when the forces on the body is zero. That's what we have learned previously. A body not in translational equilibrium will be accelerating in the direction of the resultant force. This is due to Newton's second law. So here are some examples to illustrate what I mean. Right? Let me bring out the pen. So if you look at an object on the table, it's obviously not moving. There are two forces acting on the body. First and foremost, there's the weight acting on the CG of the body. So we draw an arrow downwards. We call it weight. There must then be another force that's opposite in direction and equal in magnitude to this force of weight, such that this object on the table is in equilibrium. This force is called the normal contact force and is acting from the surface of the table upwards. See where I start the force? The length of the arrow is also about the same as the length of the weight. So it's normal contact. Sorry, it's a little bit difficult to write on the screen. Force. Right? Sometimes you have an object balanced on 2 points. Right? How would you draw the forces here? Well, same thing. We always start with weight because that's the easiest. So now let me just call it W to make my life easier. Right? And we can see the normal contact force now, there's two of them acting from the two supports on the sides. And the arrow should be half as large. There's N here. There's N here. Okay? Because these two supports are at the corners, there's a symmetry. We can see that the two arrows are about the same length. Now, what we have done for you until now is what you call a free body diagram. It's a forces acting on the body. I want to introduce to you another concept which is called vector diagram. Right? You have learned this in the first lesson you had. And you can see that if we draw the vector diagrams, we have weight here for the first case, and we have a normal contact force here. The two arrows are of the same length, and it comes back to the original point where it started, which is right here. Let's look at the other one. One more time, there's weight on the right side. Right? On the right side, there's weight. This is a vector diagram. That means we're not drawing on the body. There's a first contact force N, half the length. The second contact force N, half the length, and they go back to the original starting point, which means there's no resultant force. Right, so these are the simple examples. Let's now look at examples where the forces are not parallel to each other. One of the most common, or rather the simplest example to start with, is a body held by three non-parallel forces as seen right over here. So on the left hand side, where my mouse is, this is a diagram where there is a free body diagram showing three forces A, B, and C acting on the body. And if this object is in equilibrium, a few things must be true. Number one, the lines of actions of these forces must intersect at a point. Right? If you see, what does this mean? It means that the three forces here you see on the body A, B, and C on the free body diagram, they must intersect at the midpoint, right, or at any point, either on the body or beyond. Right? It doesn't matter. But in this case, it happens that these three forces are intersecting at a point within the body. A second thing that must be true if this object is in equilibrium is that when you rearrange the forces into a vector diagram, it produces a closed triangle. Right? So usually, right, we will do this as a first step. And the second step, to find the values of various forces. Let's say in this case, you're given the values of A and B and a certain angle between A and B. After rearranging this triangle, right, you could actually math it out. So that's actually how we solve for various forces. Right? In physics, we have many opportunities and many questions that ask for solving the values of certain forces, angles of certain forces. Right? This is the way we do it. We arrange in a vector diagram, and we use math to solve out the values of these forces. Okay. So let me give you an example now to further illustrate. Here we have a diagram, right, where a body of weight S hangs from a string, is connected to point Q in a string of P, Q, and R. If this system is in equilibrium, express the tension of PQ in terms of W, which is the weight of S. How should we do this? So first, let's start to look at body S. Let's look at body S. If we draw the free body diagram of body S, what do we get? Well, same as before, we have W. Right, so maybe here I should draw this separately to make our lives better and clearer. Let's draw body S here. Right, let's redraw body S over here. Okay, we have the weight. And here this body is held in equilibrium by a string, which means that the tension in the string, right? Tension in the string acts along the string. The length of the string does not tell you the value of the tension, but it tells you the direction. So here you have tension, and let's call this tension 3, right? Let's call this tension 3. And here we have the equation, right? Because body S is not moving, we can say that tension 3 is equal in terms of value to the weight. So this is the first conclusion that we can draw. Okay. Next, because we're going to find the value of the tension in PQ, it makes sense for us to analyze Q, because it's a common point between the weight and the string PQ. So if we look at it, we can draw the forces acting at Q. So let's start. At Q, the string is pulling downwards on Q. So we can say that there's a tension T3 over here. Change the color. There should be a force to the left. Right. Tension always acts away from the point you're considering. So let's call this T1, tension 1. Let's find another color, red maybe. And say this is tension T2. So remember, what are the steps that I recommended? First, you draw the forces. You see that they intersect at a common point, which in this case is Q. Step 2, you should rearrange it into a closed triangle. So let's do it now. Let's do step 2, rearrange it in a closed triangle. And later on, we shall then map it up. All right. So here we have T1. Then we have T2. Remember, it should be a closed triangle. And last, we have T3. Okay. And if you look at the angle here of T2 above the horizontal, T1 is a horizontal line. T2 has an angle of 30 degrees above the horizontal. We can easily add in 30 degrees as the angle here. And what have we learned about T3? Well, the value of T3 is just W. So if you want to find the value of T1 in relation to W, there is a simple trigonometric function that we know of. What is it? Tangent, right? The tangent of 30 degrees will be W over T1. So if you want the tension in section PQ, T1, we express it on the left. On the left-hand side, we make it a subject, right? We rearrange the equation, we get W over tangent 30. And that's your answer. It's as simple as this.